Let us now discuss the general concept of structure. All the structures that we have considered have the following in common. There is a universe or a domain, which is an arbitrary non-empty set. So it could be like a set of natural numbers, maybe numbers 1, 2, 5, and 7, or some words or some objects, anything. There's a great freedom in choosing the universe. Then there are some unary predicates such as red, man, whatever. There are some binary relations, also called binary predicates, such as right of, left of, greater than, smaller than, and so on. Then there are some distinguished elements such as 0, maybe also 1 or Tom or A or B. Great freedom. Names of these predicates, relations and elements constitute the so-called vocabulary of the structure. So every structure has a vocabulary. This is the first thing one fixes when one tries to define a structure for some purpose. The first thing to decide is the vocabulary. Then the universe, and then the predicates unary or binary, and maybe some distinguished element. Relations, also called predicates, are the basis of our structures. A binary relation on a set M is any collection R of elements of the Cartesian product M times M. The Cartesian product, like this M times M, consists of all ordered pairs of elements from M. Ordered pairs, like in the picture, the ordered pair A, B. So A is often called the first coordinate and B is the second coordinate. If the ordered pair AB is in R, we write ARB for simplicity. For example, if R is an less than relation, then because we write A less than B rather than the pair AB belonging to less than. In this picture, the dark blue area denotes an arbitrary subset of the Cartesian product. Examples of such relations are of course many. For example, R could be empty, then we would call it the empty relation. Or R could be the entire set M times M, and then we would call the relation a full relation. Or R could be the diagonal, all pairs AB where A equals B. Then we would call it the identity relation. Or R could consist of just one single point in the Cartesian product M times M. Then we would call R the singleton relation. Or R could be just a vertical line, all pairs where the first coordinate A is a fixed element C. We would call this the first projection relation. Or it could be a horizontal line, all pairs AB where B is a fixed element C. We would call this the second projection relation. So these are just examples, because one can invent endless number of examples of relations. Binary relations are very common. Already among people there are many familiar binary relations such as X knows Y, X and Y are cousins, etc. Special important properties of binary relations have emerged and have been given a name, such as a binary relation is called symmetric if ARB always implies BRA. So that means that the picture of the relation is symmetric with respect to the diagonal. R is reflexive if always ARA. Every element is in relation R with itself. In terms of the picture, it means that the relation contains the diagonal of the Cartesian product. Bit more complicated is the concept of a transitive relation. A relation is transitive if A are B and B are C imply A are C. A typical example is less than relation among natural numbers, because if A less than B and B less than C, then A less than C. So order relations are usually transitive. Antisymmetric relations are such that if A are B, then not B are A. Again, typical examples are strict order relations, A less than B, because if A is less than B, then certainly not B is less than A. Finally, anti-reflexivity means that A is never in relation with itself. This is quite common, and also again the strict order relation less than is usually assumed to satisfy this. No number is strictly less than itself. It's useful to contemplate among people which of these properties does the relation x knows y have. Is it symmetric, reflexive, transitive, antisymmetric, or antireflexive? One can ask the same question about the binary predicate x and y are cousins. It is also useful to contemplate the relation x less than y in the structure of natural numbers. Is it symmetric, reflexive, transitive, antisymmetric, or antireflexive, or many of these? Let us now move to the concept of vocabulary. Ordinarily, the vocabulary of a language is a set of all the words that the sentences of the language are made of. In predicate logic, we use the word vocabulary a little differently, although the spirit is the same. A vocabulary is a finite collection of unary predicate symbols, which we denote P0, P1, and so on. Binary predicate symbols R0, R1, and so on, and constant symbols C0, C1, and so on. We could treat also n-ary predicate symbols for n greater than 2, as well as function symbols, but we leave these for later. In practice, one uses also other symbols for predicate and constant symbols than the ones above. A vocabulary may be also empty. It may consist of only unary predicates and no binary predicate symbols or constants. It may also consist of only constant symbols and so on. And now the definition of structure. So we assume we have a vocabulary L. A structure M for a vocabulary L is a non-empty set M called the universe of M, and a unary predicate Pm on M for every unary predicate symbol P in L. A binary relation Rm of M times M for every binary predicate symbol R in L. And finally an element Cm of M for every constant symbol C in L. So the universe determines where those predicates are. If the universe is M, and the universe can be any non-empty set, then the unary predicates are subsets of M, the binary predicates are on M, and the elements are on M. Everything takes place in this one universe M. One could also consider several universes if the objects that we're interested in are of a very different nature. But we will not treat that case, although it can be treated in the same way as this. A common notation for structures is the following. So if the vocabulary consists of just one unary predicate P, then we denote the structure as an ordered pair M, PM. This is very common notation. If the vocabulary consists of a unary predicate P and a relation R, then we use a triple to denote the structure M, PM, RM. If the vocabulary consists of PR and a constant C, then notation for the structure is quadruple M, PM, RM, CM, and so on. The pattern should be clear. So we write in parentheses first the universe and then all the predicates and constants that arise from the vocabulary in this structure. So here is a general picture of a structure. There is a universe, which is this oval or ellipse, and there is a great freedom in choosing the universe. The universe has or may have some constants, it may have some binary predicates, it may have some unary predicates.